This video will show you an example of how to do the calculations for Lab 2. So if you remember, there were 3 parts. In the first part, we measured a rectangular solid, which was actually a popcorn box. These were the dimensions. We had 15.71, 10.80, and 5.18. And as a reminder, I would like you to estimate to the 100th place. So here's the tenths, the 100th place here, because on a ruler, if we look closely, trying to focus, if we look closely, you can see that between the major markings for centimeters, there are 10 lines. One of them is a little bit larger to show you the halfway point, and then the rest of them show you the centimeter divided into 10 portions. So actually there are 9 lines drawn in. So what you can do is, when you're measuring, you can determine which line your object meets, and then imagine that between the 2 lines that you're looking at, there's another division of 10, and that would be the 100th place in our decimal places. So you'll be estimating if your object hangs about halfway between 2 lines, where my pen is, you could say that would be 5 100ths. If it hangs a little bit more over, you could go up higher than 5. This is our practice with estimating. So make sure that you include 2 decimal places. And when we calculate the volume, you have to do length times width times height. And I noted earlier we need 3 significant figures because our measurement with the fewest is here. This has 3 significant figures. So we really just have to multiply the 3 numbers by each other. 15.71 times 10.8 times 5.18, and we get 878.88. And if we're going to round that to 3 significant figures, I'll just write the number. Our 3 significant figures will be the first 3, and we look at the one just after. It's above 5, so this bumps up to 9. So 879 cubic centimeters. That would be an example calculation for part 1. Now in part 2, all you did was measure volumes in 3 graduated cylinders or in 3 containers that held liquid. So we don't have any calculations there. I'm just going to be looking at the pictures you send me of your measuring devices, and I'll be looking at your estimations to make sure that you use the right number of significant figures in your estimations. So now for part 3. Really, the calculations are pretty simple. You have a whole data table that you can fill out, looking something like this, although mine's been filled in, so I'm going to just do an example here. So you have to find density, and as I showed you, we measured 6 grams and 8 milliliters for the mass and the volume. So we can calculate the density of that by doing 6 divided by 8. Using my measuring device, I was only able to use 1 significant figure for each of those measurements. You may have something more precise, so make sure that you use the correct level of precision for your measuring device. So our density here is 0.75, and I'm going to note that down. So if we want to, you're going to be doing 3 trials. So my density trial 1 was 0.75 grams per milliliter, or the other way to write that is 0.75 grams per cubic centimeter. That's how we talk about a solid. And for your 3 trials, you're going to determine 3 different densities. So I did 1 as an example, but let me just give you example numbers to work with. Let's say the next one I found 0.8, and the final one I found 0.65, just for an example. Okay, so now what you have to do is find the average, just like we did in Lab 1. So to do that, you're going to add all 3 numbers together, so 0.75 plus 0.8 plus 0.65, and then divide by the number of samples. You have 3 samples. So your average is 0.73 repeating. We're going to keep 2 significant figures. So we have 0.73 grams per centimeter cubed. And does this number represent well our whole sample set? Yes, I would say it does. Always check. Make sure that your average is similar to what you've shown here. If it's a lot bigger, like for example 2.2 like I had before, you know you've just forgotten to divide by 3. That's a common mistake. Okay, so now we have our average, and then you have to go online and look at supplementary videos and resources and click on the resource to locate the density of the food that you've chosen. So I measured black-eyed peas. So I would look up the density of that food. So let's say that that density was something like 0.70 grams per cubic centimeter. What I have to do now is calculate the percent error. And that represents the difference of your measurement to their measurement. So basically what we have to do is take your measurement, which in our case was, that's what we measured, 0.73. Subtract it from 0.7, that's the theoretical value. That's the one that we looked up on the internet. I just gave that to you as an example. And we're going to divide that by our reference value or our theoretical value. They can be called either. So basically we're saying how far apart is one from the other. You can see it's 0.03 grams per cubic centimeter. And then we want to know how much of that whole original measurement does our difference make up. And we're going to represent that as a percentage by multiplying by 100. And there's our formula for percent error. This is also in your lab book. So to calculate it, the first thing you have to do is solve within the parentheses first. So we have 0.03 on top. If this number was smaller than this number, you can have a negative sign here. You can have a negative sign. So if your measurement was smaller than the reference value, you'd end up with a negative percent error. That's just fine. All that tells you is that your measurement was smaller than theirs. And then we divide by 0.7 and multiply by 100. So what we have to do is our division first. So we'll do 0.03 divided by 0.7, and then we can multiply by 100. So I'll note that here just to show the step-by-step process. I'm going to keep one significant figure because that's all we have left here, and then multiply by 100. Actually, this is an important part. Once you do subtraction, you end up with a number that has a lower number of significant figures than you started with. This has 1. This has 2. So we're going to go with 1 in the end. So we have 0.04 times 100. We end up with a 4% error. And that is pretty good. If you read in your lab manual, a percent error of less than 5 is excellent, and that's what we're looking for. So just see what you find. It's okay if your percent error is off by more than that. I won't take points off, but make sure that you do your calculations correctly, pay close attention to significant figures and to all of your measurements. I'm really paying attention to significant figures as we're learning about that in Chapter 2 right now, and that will carry out throughout the whole semester. So that's how we do our calculations. And make sure you answer all the questions on your data sheet included in the lab manual, and you upload a clear picture of them to Blackboard for me, along with some clear pictures of the lab experiment that you carried out, or a video. I prefer a video if possible. That would be great. Okay, happy calculating.